series on cryptocurrency. How SPV nodes use Bloom filters. Bloom filters are used to filter the transactions and blocks containing them that an SPV node receives from its peers, selecting only transactions of interest to the SPV node without revealing which addresses or keys it is interested in. An SPV node will initialize a Bloom filter as empty. In that state, the Bloom filter will not match any patterns. The SPV node will then make a list of all the addresses, keys and hashes that it is interested in. It will do this by extracting the public key hash and script hash and transaction IDs from any UTXO controlled by its wallet. The SPV node then adds each of these to the Bloom filter so that the Bloom filter will match if these patterns are present in a transaction. Without revealing the patterns themselves, the SPV node will then send a filter load message to the peer containing the Bloom filter to use on the connection. On the peer, Bloom filters are checked against each incoming transaction. The full node checks several parts of the transaction against the Bloom filter, looking for a match including the transaction ID, the data components from the locking scripts of each of the transaction outputs, every key and hash in the script, each of the transaction inputs, each of the input signature data components or witness scripts. By checking against all these components, Bloom filters can be used to match public key hashes, scripts, OP return values, public keys in signatures or any future component of a smart contract or complex script. After a filter is established, the peer will then test each transaction's outputs against the Bloom filter. Only transactions that match the filter are sent to the node. In response to get data message from the node, peers will send a Merkle block message that contains only block headers for blocks matching the filter and a Merkle path for each matching transaction. The peer would then also send TX messages containing the transactions matched by the filter. As the full node sends transactions to the SPV node, the SPV node discards any false positives and uses the correctly matched transactions to update its UTXO set and wallet balance. As it updates its own view of the UTXO set, it also modifies the Bloom filter to match any future transactions referencing the UTXO it just found. The full node then uses the new Bloom filter to match new transactions and the whole process repeats. The node setting the Bloom filter can interactively add patterns to the filter by sending a filter add message. To clear the Bloom filter, the node can send a filter clear message because it is not possible to remove a pattern from a Bloom filter. A node has a clear and resend a new Bloom filter if a pattern is no longer desired. The network protocol and Bloom filter mechanism for SPV nodes is defined in BIP 37 peer services. SPV nodes and privacy. Nodes that implement SPV have weaker privacy than a full node. A full node receives all transactions and therefore reveals no information about whether it is using some address in its wallet. An SPV node receives a filtered list of transactions related to the addresses that are in its wallet. As a result, it reduces the privacy of the owner. Bloom filters are a way to reduce the loss of privacy. Without them, an SPV node would have to explicitly list the addresses it was interested in, creating a serious breach of privacy. However, even with Bloom filters, an adversary monitoring the traffic of an SPV client or connected to it directly as a node in the P2P network can collect enough information over time to learn the addresses in the wallet of the SPV client. Encrypted and authenticated connections. Most new users of Bitcoin assume that the network communications of a Bitcoin node are encrypted. In fact, the original implementation of Bitcoin communicates entirely in the clear. While this is not a major privacy concern for full nodes, it is a big problem for SPV nodes. As a way to increase the privacy and security of the Bitcoin P2P network, there are two solutions that provide encryption of the communications: Tor Transport and P2P authentication and encryption with BIP 150/151. Tor Transport. Tor, which stands for the Onion Routing Network, is a software project and network that offers encryption and encapsulation of data through randomized network paths that offer anonymity, untraceability and privacy. Bitcoin Core offers several configuration options that allow you to run a Bitcoin node with its traffic transported over the Tor network. In addition, Bitcoin Core can also offer a Tor hidden service, allowing other Tor nodes to connect to your node directly over Tor. As a Bitcoin Core version 0.12, a node will offer a hidden Tor service automatically if it is able to connect to a local Tor service. If you have Tor installed and the Bitcoin Core process runs as a user with adequate permissions to access the Tor authentication cookie, it should work automatically. Use the debug flag to return on Bitcoin Core's debugging for the Tor service like this: $Bitcoin daemon debug equals T. You should also see Tor add onion successful in the logs, indicating that Bitcoin Core has added a hidden service to the Tor network. You can find more instructions on running Bitcoin Core as a Tor hidden service in the Bitcoin Core documentation docs/tor.md and various online tutorials. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.